इनको भी इधर ही आके भौंकना है। Standard 10 Physics, Chapter 2, we are going to see today work, power, and energy. So, these three physical quantities we are going to discuss in detail along with the mathematical working work, power, and energy. So, to start with, what is work? I have written in the questions form so that you can directly learn them, right? You can grasp them up, understand, and then grasp it so that during exam you can write it in your own words. So the first one we have is what is define work, right? So how do we exactly define work? So work, it is defined as when a force or its component causes displacement in direction of force or its component, work is said to be done. In our everyday life, right, we carry out daily activities. Let's say sweeping a floor, let's say taking books from the bag, keeping it into the cupboard, playing, right, carrying objects from one place to other place. So in practical life, the work done psychologically, it is different, but when we come to the physics, right, the measurement of the work done, right, whatever activities you carry out, how much work exactly you do, apart from describing your work in words, right, we will describe work done mathematically, that is exactly in terms of digits. We will find out that what is the work done. So define, we have force or its component. The work component holds importance. We have other topic in which we will be discussing what exactly do we mean by its component, right? Causes displacement, the object change its position from one to the other, right, in the direction of force or in the direction of its component, we say the work is done. So in terms of physics, when the object gets displaced, right, it was here and now it gets displaced here in the direction of the force, then we say the work is done. That is a theoretical explanation, and then we also have a mathematical expression. In order to understand work done, the physical quantity work done, right, we have these examples. The first one we have, whenever you see there is a change in shape or size, right, you can say that yes, the work is done. See the object, heavy object placed on the spring, as a result of which the size of the spring gets compressed, it gets little shorter than the original one, we say the work is done. As soon as you remove this load, spring expands, overshooting its original position, right? Original shape may be this one till here, but as soon as you release the spring, due to inertia of motion, it will overshoot and come to the some new position. So once again the work is done. There is a force. When you compress the spring gives a opposing force, right? It want to expand, and when you expand a spring automatically it has a property to contract. It's because of its shape, it's because of its structure. So compressed spring when released does a work on the ball. Kids sitting at a place and making different shapes of object with the help of the plasticine, maybe some sort of clay, they are doing work because they are changing the shape of the plasticine. So again, when the change in shape is there, we say the work is done. Change in size, that is the length may change, area may change, again the work is done. Change in speed or direction, again the work is done, right? A object was moving, let's say ball was moving and you kicked it, so its speed changed, ultimately the work is done. and even if the direction is changed, right, the ball was traveling straight, hit by the batsman, it reverses its direction. So once again the work is done. Change in position, right, the object was somewhere here, you pushed it, its new position is now B. So again there is a displacement, for sure it has been caused due to some force. So work is done. Towing a car, right, crane pulls away the car to the new position, once again the work is done. So that is the theoretical understanding of the work done, right? Let's see next, factors affecting the work done. What are the factors on which the work done depends? So work done depends upon two factors. The first factor, we have that work done is directly proportional to the force. More the force, more is the work done. And work done, it is also directly proportional to the displacement. More the displacement, more is the work done. You carry object from here to here, yes, you have done the work. But if you carry object from here to here, more displacement, more work done, right? You apply with the force, you apply force with the one hand, and instead other way around, you apply force with both the hands. So if you increase the force, work done will be more. If you increase the displacement, once again the work done will be more. So these are the two factors on which the work done depends. Both are directly proportional. That is nothing but if the force increase, ultimately the work done also increases. Once again, displacement is more, work done is also a more. That is the meaning of a directly proportional. Then the mathematical expression for the work done. How do we describe the work done mathematically? So from the factors itself, right, from the factors itself, we know that the work done is directly proportional to the force. Force is a vector quantity, so we represent it with a vector sign. Work done is also proportional to the displacement. Displacement is also a vector quantity, we represent it vectoritically. Ultimately work done is proportional to F dot S. Dot is a special type of a product, it's not a conventional product that you carry out. 2.3, that is 2 multiplied by 3 equal to 6. But when we deal with vector quantities, dot have some specific meaning, it has some detailed meaning. As you go through the standard 10, right, you move on to the 11th standard, step by step you will learn the details of vectors. So within the vector mathematics, the dot multiplication holds lots of importance. Other multiplication which you will see will be R cross F, that is the torque, right? Torque is obtained by cross multiplication of the perpendicular distance and the force. So here once again the cross product has got some detailed rules. As you go through, right, you will get to know what exactly cross product it means, what exactly dot product it means. Here if I solve it further, the torque, it can be given by Rf sine theta. So when the dot cross product gets removed, sine theta appears. Here if we work further, is equals to K F dot S. The value of K is always 1. K is constant of proportionality. So work done, we will have F dot S. This is a vector equation, and the same vector equation can be written as Fs cos theta, a scalar equation. This is a vector equation of the torque, and here we have a scalar equation of the torque. So just note the difference when the dot product gets removed. Now here we don't have anything between them, so that is nothing but they both will be multiplied as they with the conventional methods that you have learned in maths till 10th standard. So further, if you want to write it in more details, it is written as modulus of S cos theta. That is, modulus means only magnitude we consider, Same way here also it is modulus of R, only magnitude of the force. This equation has, since it is a vector equation, it has got both magnitude as well as direction. Same way here also, vector equation, this equation has magnitude as well as both direction. Both cannot be calculated simultaneously. First you calculate work done, first you calculate magnitude, and then you calculate the direction. So this formula will give you magnitude, This part cos theta, it will give you the direction, the resultant direction. Let us see how. So mathematical expression for the work done from the factors, right? We have found out the formula of the work done, a vector equation, right? And this one we have a scalar equation. And in order to understand the dot and cross product, I have given this example. This is once again a vector equation and this is a scalar equation. Let's see some examples which help us to understand the work done. So let's say you have been given an object, right? Let's say the object, it has its mass 10 kg and you apply a force of 12 newtons. Now because of the force, the object gets displaced to the new position, and let's say this displacement cost is 5 meters. What is the work done? So we'll use the equation F as cos theta. This is the formula, F as cos theta. No need to mention such things always. Such symbols are always not necessary. You can in simple way write down cos theta. So what is the force used here? 12 newtons. What is the displacement cost? 5 meters. And what about the theta? Theta, it is the angle between force and displacement. Force and displacement. You can see here the force is also in same direction as well as displacement is also in same direction. So angle between them is 0. So theta is 0 over here, cos 0. So 12 5s are 60 Newton meter is the work done. Other name for the Newton meter is joules. A simple word. Joule was the name of the scientist who discovered a steam engine. So to respect him, we have a unit joule. One more example. Let us see. Let's say you have a box over here and you are applying the force of, let's say, 12 newtons, right? And this force, instead of moving towards the right direction, it gets displaced to the left direction. The displacement cost to the left direction is 5 meters. See, you are applying force from left to right. The direction is left to right, but the displacement is taking from right to left. So once again, if we apply the formula F as cos theta, force was 12 newtons, displacement is 5 meter. You should learn to write down units along. It will help you to understand things better, solve it in a better way. And about theta, so theta we can see displacement and force. Displacement is towards the left and force is towards the right. So the angle between them is 180 degrees. So it will be cos 180. So this will be 60 Newton meter. Cos 180 is minus 1. So minus 60 Newton meter. The work done is negative. Negative sign, it clearly shows that work is done against the direction of the force. Negative sign means work done is against the direction of force. And here also you can write down, since the work done is positive, you can say that work done is in the direction of force. So this is a basic explanation of the formula F as cos theta. We have many more cases we'll discuss next. And then we have right, we had seen the mathematical expression and I was showing you the example how to use F as cos theta. Then next we have components of the force and work done. Now here we had seen that we have a word right in the definition, that force and its component. So the examples which we have seen were the very simple examples, right? Work done and force, they are in same direction or they are in opposite direction. But what, instead of same or opposite, if any other angle is given, then you can see here the man is pulling a lady in the cart, but the angle at which he is pulling is making a 50 Newton. So here in this case, what to do? Now see, this force, we want force should be in the direction of the displacement. We want this force. We have nothing to do with this. But how do we get F1? From F itself, we get a F1, right? We will call the component of the force. F1 is a component of the force. Now let me get into the detail. What exactly do we mean by component of the force? Now this force, right? This force, angular force, this angular force, it can be converted into the horizontal as well as into the vertical form. We call these as resolving the force into horizontal and vertical component. Resolving the force into horizontal and vertical component. It's nothing but when the force acts at an angle, it has its magnitude horizontally as well as it has its magnitude vertically also. Once again, whenever such situation you see that force is acting at some angle, simple conclusion is that force has its component in the horizontal direction as well as vertical direction. So the value of the force is given as 50 newtons. So this 50 newtons gets divided into two parts, horizontal as well as vertical. How do we calculate the horizontal component, that is F cos 30? And how do we calculate the vertical component, that is F sin 30? There is a physics behind it, how these things came, but those things falls into the details of vectors. So you can go to the lecture of vectors and see how the components of the force are obtained in detail. As of now, just remember that the force which acts at an angle has its component in horizontal direction as well as in a vertical direction. How do we get a horizontal component? F cos theta, and vertical component as F sin theta. So exactly as per this example, if we calculate, it will be F is 50 and cos 30 we know it is root 3 by 2. So we get as 25 root 3 newtons. You can calculate further if you want. And F sin 30, so F is 50 and sin 30 is 1 by 2. So we have 25 newtons. If we simplify further, that is 25 into root 3 is 1.732. So let's say I just multiply it with the 1.7. Right, so 42.5 it is. So just when you add 25 root 3, 1.732, so it becomes 42.5 newtons. So this 50 newtons get resolved as horizontal value will be 42.5 and the vertical value will be, we have 25 newtons. Just note this. Now here the question may arise that why F is not equal to FH plus FV. Once again the answer is vector mathematics. In vector mathematics, simple additions are not done. There are some rules to add the vector quantities. As I said, vector mathematics completely, it's a bigger topic. Just for the sake of 10th standard, right, you can remember this. So components of the force and the work done, if I present it, if I write it exactly in an answer way, this was to discuss the example. I'll write it down over here, that if in case it comes into the exam, how will you represent? So component of the force you can write down as let F be the force acting at angle theta with horizontal. So the diagram would be somewhat like this. F acts at angle theta, right? Hence, FH, that is the horizontal component of the force, and FV, which is the vertical component of the force, it is given by F cos theta, and vertical component is given by F sin theta. In case an alternative to this, that if instead of horizontal, if the angle is given with vertical, then what to do? So I'll write it down over here, that here we have some space, so let's utilize. So in case if the angle is given with the vertical, right, F, and if this angle is given, so FV will be F cos theta, just see this, and FH will be F sin theta, see this, right? So wherever you have theta, that component comes with a cos. See, we have a theta with horizontal, so horizontal component comes with a cos. Here we have theta with the vertical, so vertical component comes with the cos. So this is the answer to this question, component of the force. And as per this component, then further you can write it down as that, therefore horizontal work done will be equal to F cos theta into the displacement that is caused horizontally, let's say SH, and work done will be F sin theta if the displacement caused vertically is, let's say, SV, right? So perpendicular direction we have displacement caused SV, and horizontal direction we have displacement caused SH. You must add a line over here. I'll write it down here, that let SH and SV be displacement in horizontal and vertical direction respectively. So this is the case. Next, if we move on to special cases of work done, right? Now depending upon this theta, we can classify the work done into three cases. One is positive work done, other is negative work done, and the third one we have zero work done. So this fifth one, positive work done. So these cases which I had done were the simple ones, in which the force and displacement are both either horizontal or either both of them are vertical, or both of them are horizontal. This is the simple case. This was the case, this one, right? Force and displacement, they both are in the same direction horizontally. I have not taken any example of the angle, and this is the case when the force and displacement are opposite. So both horizontal, either in same direction or in opposite direction. And as per this concept, right, as per this concept, we'll see, here is the one example when the force act at some angle, the work done in the horizontal direction, right, I have calculated, that is 42 point, no, here the force is only calculated. You can calculate the work done further. So if I want to calculate work done in the horizontal direction, so horizontal direction, so I'll take force in the horizontal direction as well as displacement in the horizontal direction. Horizontally, This trolley is not moving anywhere. So ultimately it is 0. So FH into 0, work done in the horizontal direction is 0. If I calculate the work done, sorry, this is about the vertical direction. Horizontal direction, we have been given displacement. Displacement in the horizontal direction, they've said it is 30 meters. And we also have a force in the horizontal direction, that is 42.5. So 42.5 is the force and displacement is 30. So we have 127.5 joules. This is the work done horizontally. But if you see vertically, the work done in the vertical direction, so it will be vertical force and vertical displacement. Vertical displacement is 0. So ultimately work done in the vertical direction is 0. So this is how the work done works with the help of the component of the force. In order to find out the work done, in order to use the formula, right, you should know, first you should be very clear about the force. It should be either horizontal or should be vertical. In case if the force is at angle, find its horizontal and vertical components. Then identify the displacement in horizontal and vertical direction, and then calculate both the work done separately. So these are the three different cases to calculate the work done. One is both of them are in the same direction. This one, both of them are parallel to one another. Both of them are horizontally, either in same direction or opposite direction. And this is 1 and 2 case, and the other case is when the force is acting at a angle. So this is the step. When the force is acting at an angle, step number 1 is find horizontal and vertical components. Step number 2, identify horizontal and vertical displacement, horizontal displacement and vertical displacement. And step number 3, calculate horizontal work done and calculate vertical work done. Next, let us see the answer to this question is only this white part, right? Other part is the explanation to the concept. Next, we have special cases of the work done, right? Positive work done and negative work done. So we have 5.1 as a positive work done, and we have a 5.2 as a negative work done. Yes, this is another example to understand the F cos theta, the use of the formula. We'll come back to it. First, we'll see positive, negative and zero work done. Yes, zero work done is present over here. So positive work done, it is when the angle is 0 degree. We know the formula. Work done is Fs cos theta, right? When theta is equals to 0 degree. Theta is equals to 0 degree. It means, if we write it in words, force and displacement are in same direction. Force and displacement are in same direction, right? Then work done is positive. Work done is positive. You can also say maximum work done is Fs. This is the maximum work done, as the value of cos 0 is 1. So when both are in the same direction, maximum work can be done by the given force as compared to any other situation. When force and displacement are in the same direction, you will get the maximum work. You can see here. See this one, when both of them are in the same direction, right, work done is plus 60 joules, but when both of them are in the opposite direction, negative work done it is. The magnitude is same, but the directions are opposite. Negative means it's smaller, positive means it's larger. Work done. Then negative work done. So once again, starting with the formula, we know that work done is given by Fs cos theta, right? When the value of the theta is 180 degree, right, work done will be Fs cos 180. Cos 180 is minus 1, so work done is negative. Negative work done. negative work is done, right? So it is nothing but when theta is 180 degree. Again in words, force and displacement are in opposite direction. Both are exactly opposite to each other. And then the third one we have work done is 0. So we again starting from the formula, we know that work done is Fs cos 180 when theta is equals to 90 degree, right? Work done will be Fs cos 90. The value of cos 90 is 0. So ultimately work done will also be 0. So this is the example of 0 work done. If I represent it diagrammatically, it would be somewhat like this, that the displacement, right, and this is the force. See, both of them making 90 degree to one another. Another diagram that is possible will be this way. See, 90 degree, once again force and displacement are making 90 degree to one another. It doesn't make any difference if you exchange their positions, right? Force if you take it here, displacement if you take it here, but there should be 90 degree between them. Other case, right, here if I represent it diagrammatically, right, the angle is 0. So force as well as displacement, they are both in the same direction. See, the angle between them is 0. The box is pulled with the force F, ultimately the displacement also happens in the same direction. And here in this case, diagrammatically if I represent, right, let's say box, force is in the right direction but displacement takes place in the left direction. The angle is 180 degree. So positive, negative and the 0 work done. Positive work done when force and displacement are in the same direction. Other way round, angle is 0 degree. Other way round, both of them diagrammatically appears this way. So either from the theta or from the inspection of diagram or from the words written in the question, you should identify whether it is positive work done, what is the angle, positive work done, negative work done, and finally the 0 work done. Next we have units of the work done, right? So once again from the formula itself we get the units. We have formula as Fs cos theta. So force SI unit will write down. Force is measured in terms of Newton, displacement is measured in terms of meter. So SI unit is Newton meter. Newton meter can also be written as joule, right? If we write it in fundamental form, in a fundamental form, if we write down, fundamental form means in the terms of mass, length, time, temperature. So Newton will be multiplied by meter. Newton is nothing but force. Force is ma. M for mass kg, a acceleration, meter per second square. So fundamental form is kg meter square second square. This is the fundamental form of joule. And same way, if I write down the CGS unit, right, it will be Dian centimeter. Dian centimeter, we don't have any short name for it. We just call it as a Dian centimeter. And fundamentally, if we write down the CGS format, right, it will be Dian means the same things but converted into CGS form. So kg becomes gram, meter becomes centimeter square, and second square as it is. So this is a fundamental form of CGS unit, work done. Then yes, here we have its part. Dian centimeter is also called as org. Sorry, Newton meter in short it is called as joule, and Dian centimeter is called as org. Next question we have is relationship between the joules and org. So how will you find out 1 joule is equals to how many org? So to begin with, joule, write it in its fundamental form. It is 1 kg 1 meter square divided by 1 second square. 1 kg can be written as 1000 grams. We want a CGS format, right? Joule is a SI format. We want CGS format. So convert this into CGS form. So 1 kg becomes gram. 1 meter is 100 centimeter, and we have a square over it, and 1 second square as it is. For time, CGS and SI formats are same. So this becomes 1000 gram. 100 square will be 10 to the power 4, right? Two zeros and power 4 centimeter square upon second square. 10 to the power 4 and these three zeros becomes 10 to the power 7 gram centimeter square upon second square. Gram centimeter square upon second square, it is nothing but a org. So we clearly have that 1 joule is 10 to the power 7 org. This question can be in the derived form or just can be for 1 mark also.